Hey, how's it going, everyone? Happy New Year! All right, we're on to a new. We're in 2026. Well, at least for me, 2026 is in a few hours from now. For a lot of everyone in the world, 2021 or 2026 is already happening. It's already happening. It's the new year. We're going to be reviewing Neva's code changes to our click predictor. Neva said that it works amazing. The amount of accuracy that the click predictor now has is stunning, and I'm really excited to see what are the differences that have been made. And I'm seeing a few things. So I see a comb in here, an act. I don't know what an act is. We're gonna take a look. We're going to merge these changes, and then we're going to see what it's like, and we're gonna run it locally. We're gonna try it out, and then we're gonna walk through the code changes. I'm really excited about this. I think it'll be really neat. Really neat. Okay, let's go ahead and merge these changes here. Oh wait, it's not. This might be too much. Wait, this branch has conflicts. Okay, let's resolve the conflicts. All right. Well, let's see. Which one is bigger? Which one has more? All we have to do is look at the line that has more here, and we'll resolve those conflicts. Okay, the top one. Okay, so we'll use the top one. Okay, close this. Close that. Get rid of that. Okay, done. Markers resolved. Oh, is there some? Oh no. All right. So, that's way too many. That is way too many. That's weird. Okay, we'll go through this. We'll walk through it. Accept changes, accept incoming changes, accept both changes. You can do both. Hey, Neva, how's it going? Steven, that's not the good branch. Oh, it's not the good branch? Oh, thank you for saying something early. Which is the best one? Oh, so not the heat map branch. Okay, so hey Doba, how's it good? Good to see you. Happy New Year. Happy New Year. Perhaps we're walking through Neva's source code. All right, so there's another branch you say. There's another branch. All right, so maybe what we could do is we'll go through. Let's see if we'll go through your. Let's see. Oh, wait, we need to go over to your fork. We'll go over to your fork. Minimal is the best by far. All right, let's go to minimal. All right. So I want to go to pull requests, and we'll go over here to heat map, and then we'll click on your version over here, and then we go to minimal. Excellent. And then what I'm going to do is we're going to go ahead and clone your repository, and we will load it locally, and we'll say over here, we'll just do this. Git clone cd click. Oh, that's excellent. There we go. Okay. Close this. CD. Hey, how's it going? Just a random. How's it going? Hey, we're going again. Feels so heartwarming to see you work every day. All right, thank you. I mean, here's night. Yeah, we're here. Happy New Year. You'll PR. It's really different. All right, sounds good. I found your minimal branch. Minimal branch. Hey, Zers. Hey, Zersis. Hey, Steven. Good to see you. Happy New Year. We are on our way here. What we're going to do is get our code branch in the minimal branch from Neva. Neva has done some really amazing work. I'm really excited about this. We're going to walk through all the code that Neva has done for us, and we're going to see. Apparently, it's amazing. By the way, if it's slow, turn on the compile. Oh, you have a 4090, so it's pretty fast. All right. It should be pretty fast for me. My accelerator works really well if the batch sizes are large. So I've got if the batch sizes are large, it's good. Because it works pretty well overall though. I've noticed that the larger the batch sizes, the faster it goes. So let's see here. Where are we? CD click prediction AI. All right. So this will be, let's see. I want it to call this window the Vim Neva's code. Okay, vi main. Okay, and we'll go over to this one and we'll say run Neva's code. Excellent. There we go. I'm gonna try it. We're gonna try running it. I'm pretty sure it'll work, right? I'm pretty sure it'll work. Hey Torva, how's it good? Good to see you, Torva. Welcome on in. Happy New Year. Good to have you here. Hey Savon, you're gonna watch the ball dropping in New York Times. Happy New Year, Steven. Thank you. Yeah, Happy New Year's. I started with 128. That sounds good, 128. And now at 64. The thing is that 48 iterations, so asking a lot in 7 seconds. That's totally fine. I think that's fine. Happy New Year. Happy New Year. All right, where are we at here? So let's do Python main. All right, let's see what this looks like. All right, let's see. All right, here it goes. It's off to the races. Oh, hey, we're getting some jump arounds there. We're getting some jump arounds. Is it working? Is this, I'm on the minimal branch. Is this the right, does this look correct? Does this look correct? I think it does. It looks exactly the same as it, wait, is this even the right, is this the right one? Hold on a second. Yeah, this is, so get stats. Oh, wait. We need to check out the branch. Get fetch all. Get check out origin minimal, right? Get check out dash B minimal. Excellent. All right, now I was like, this looked like it used to be before. I'm like, I'm not noticing anything different. It's because we were on the branch. Get status. All right, get branch. All right, so we are on the minimal branch, as you can see here, right here. Minimal branch, right there. Minimal branch. Okay, let's try it again. No, you made a new branch called minimal. Oh, I did. Well, that's actually fine. That's actually fine because I did pull it. So get log. Here you go. Here's your log. So this shows us that we're on the correct place right here, right? This looks correct. Stabilized lost, more models, adjusted learning rate. Let's validate this. Let's look this. So this is the minimal branch, and we'll look at all the commits. Let's see if the messages are right. Stabilized, lost, more models. Yep, there we go. We're on the right track. Yes, that's the one. All right, we did it. We're there. We're making things happen here. All right, so let's try it. Python main run. Okay, pull it in. All right. Oh no, instant failure. Cannot convert MPS tensor to float64. D-type on MPS framework doesn't support float64. Please use float32 instead. Okay. Solved. It might be. We just have to do a little bit of change to work on my particular accelerator. We have to make some changes on my accelerator. I need float32. Float64 is too much. All right. So let's try this. Main float64. And we'll just change this to 32. Is that going to do it? I don't know. Oh, just remove it's fine. All right, yeah, we'll see. I'm pretty sure that's all we had to do there. I hope. Hey, there we go. There we go. Look at that. All right. Is it predicting? It looks like it's getting pretty close. Let's look at the loss here. Look at the loss on the screen. It looks like it needs more training because the loss is doing okay. Oh, it's dropping. It's dropping. We need like an average train. So is that a batch loss? We'll have to look at it. We'll have to read the code. I was thinking I got numerical stability problems on the weights. It was the loss being too close to 0. Oh, really? That sounds like a good thing. You want the loss to be 0. Ooh, the click is actually going. Oh, look at that. Ooh, look. Ooh, this is great. Oh, wow, look at how good that is. Okay, you can visually see that it's looking pretty good. It's looking pretty good. See where the magenta dot is actually going underneath. We need to make the magenta dot bigger so we can more easily see it because now it's actually going underneath the click locations. Isn't that amazing? Neva, you've done some good work here, Neva. You've done some phenomenal work. So we tied up the algos and type of neural network. Yeah, we're going to walk through that. We're going to walk through it today. I'm actually really excited to see what Neva's done. Looks pretty. It looks like it's pretty good. It's a lot better than where we've had before. And look, actually it is jumping around. It's jumping around, predicting where the next click is going to be. This is exactly what I was hoping for. So let's walk through it. We'll walk through it. I think you want to compile it. There's a line in there that turned, but for hardware, it seems a bit slow. Okay. We'll do a compile. How big are the batches? Okay. Compile. Where is it? Right here. Here we go. Is that the only one? Okay. Compile. Okay. Let's see if it goes faster. It does not like it. It doesn't like it. All right. Compile is not supported on 3.14. Oh, no. Well, that seems like the problem. What version does it want? So what I could do is say deactivate. Thank you for the heart. Thank you for the floaty heart icons. Or AB Productions. How's it going? What's up? Happy New Year. Good to see ya. We're walking through Neva's source code for the AI click predictor, and it actually works now. It actually works. It actually is predicting where the UX user is clicking. And today the plan is we're going to walk through all the code. Obviously, it's broken right here, so we're gonna make a few changes. Oh, Steven, doing rookie mistakes? Yeah, I know. You want to install 312 on all the Pytorch projects. Okay, 312. Got it. Good news, I already have it. Source VM 312. I've got it already. Bin activate. Oops, no, activate. Activate, thank you. Okay. And then pip install torch and torch vision. I think that's all we got to do. All right, looks like we're already satisfied. Let's try running it. Let's see if it works now. Oh, Pygame, we got to do that, Pygame. Pip install Pygame. Okay. All right. Good news. All right, let's see if it runs now. Let's see if it runs. Hey, it's looking good. It's looking, maybe. It's compiling. Okay, it's compiling. I'm pretty sure it's compiling, right? It's doing all the things to make it faster. Let's see if it's looking good. Is it running? I can't tell. Is it working? I don't know. Oh, there it goes. Okay, good. All right. It, for whatever reason, actually seems like it's a lot slow. Well, okay. It seems like it's the same speed as it was before. Oh, although the clicks are doing pretty good. Look at those clicks. Look at those clicks. Look at the clicks. Oh, that's so good. Oh, the tracking is just about almost spot on. All right, it needs more. Steven, what's your resolution or plans for this year? Well, I want to make sure that I've got enough streams going. Is that working? Is it still going? Yeah, okay, still going. It's still going. It looks like it's actually a little slower for maybe because 314 is so much faster than 312. Potentially. I don't know, but those clicks are really good. Oh, that's so good. It's so good. So yeah, Shyam, New Year's resolution plans. This is we make sure we hit all of our streaming days, Monday through Friday. That's what I want to do. What's our definition of done? Maybe we can see some similar data sets, slow motion play to see how good predictions are. Yeah, so definition of done is when, after it's done training here, we will try some clicking patterns. And if it predicts my clicks, I think that counts as a win. Hey, Ghost Wolf, how's it going? What's happening on the screen? So what you're seeing here, all the green dots are previous clicks. And the magenta dot is the dot that is predicting the next click. And you can see that very often it actually gets very close to where the click is supposed to be at, which is, I think, amazing. So this is Neva's code. We'll be walking through Neva's code. We'll see what changes were made and see maybe if we can increase the training, because I don't know how big the batches are. Hey, guess whose birthday is today, right? I know wait, is it Earth? Is it Earth's birthday today because of the new year? Is that how it is? Close the terminal window or dropping the prints. The IO is slowing the display. Actually, the IO is not going too fast. I think what the slowdown is, we'll have to look. We'll find out. I couldn't quite work out the math for a proper way to do more here. It's annoying you. I think you did a great job. I think you did a stunning job, and I'm very excited to walk through the code. As soon as it wraps up training here, I want to run some clicks myself to see how well it predicts my clicks. We'll see how well it predicts my clicks. The first few ticks are slow, then it goes fast. Got it. Yes, I was actually really weird. I was surprised to see it looked like 314 was a smidge faster, even without the compilation. Rusty Window, community hackathon this year. Oh, good idea. Yeah, we could do a community hackathon. That would actually be a great idea. Great idea. So as soon as this sort of wraps up, I'm going to see how close that magenta dot is. Oh, it looks so good, doesn't it? Oh, that's so great. Oh, Neva, you did a stunning job. This is exactly what we're looking for. You love the heat map. Looks very good. It's pretty good, isn't it? It's pretty good. You can see, and it's only 3 circles. And we could improve the heat map to make it look even better. I think it's efficient though. I think we did pretty good. Yeah, I think we did pretty good. Good idea, Savan. The heat map, your idea. We implemented it. We implemented it. Let's see here. So it's still going. So what I'm going to do is I'm going to set it aside, and then Neva needs to explain matching the neural network architecture to the problem. That would be great. Neva, anything that you want to comment on, we're going to start reading through your code. So let's let that keep running. I'm going to let that run there. And I'll keep it on screen so it looks interesting. So you can see that it's still working. And then I will go over to this over here, and we're going to start running through the code. Did it already finish? Wait. Oh, it just finished right when we were done. Okay. Now that it's done, let me bring this back up here really quick. So I'm going to bring this up so you can see. I don't know. Is that good enough? Here, I need to, I like pixel perfection. 1 second. I want to make sure that this is perfect. I think that's fine. Okay, make sure this looks good there. You can see that. Okay, there we go. Okay, good. Okay, excellent. All right, excellent. Looking good, you guys. Looking good. Okay, so, hey, how's it going, Frankie? What is this? This is a click predictor. Where I click on the screen, it tracks where I'm going to click next. Oh, did it get it? So, see how close it got? See how close it gets? It's doing pretty good. I think it's doing pretty good. Yep. It knows there. Yep, it knows there. It's good. It's pretty close. Look, isn't that good? It's like predicting where it thinks. See, that's pretty good. That's pretty good. All right, I count that as a win. I count that as victory. Neva. Congratulations, Neva. How is it beneficial? So you can use it for detecting whether a human is clicking on the screen or whether it's an AI, right? So that's one thing. Obviously, we need AI to battle AI. So there is an aspect of that. You can use it to mostly validate, and there are other applications. I'm pretty sure we could. Also, it's fun, right? Yeah, exactly. It's also just for fun to play with. It is. It's just for fun to play with. You got it. Oh, that's so good. It's so good. What if I click here and here? Yep. That's looking good. Look at that. It knows. Neva, you created one smart AI here. That is pretty neat. It's pretty good. It does a pretty good job there. Yep, there we go. Look at that. Oh, it's so good. Okay. So I count that as a win, because then what you could do is you can just calculate the distance and probabilities and the number of clicks over time and say, thank you for the heart icons. Teach you how to hack. Well, I've got good news for you, Frankie. If you are interested in hacking, there are dark LLMs, if you want, dark large language models. Wolf GPT, Femto GPT, I think. And just look up those kinds of words, and you'll run into them. And it will teach you how to do nefarious activities. If you want to do nefarious activities. All right, let's walk through some of Neva's code here. Okay, so we compiled it. Teach me. I know, right? We could. There's a lot of things. It really depends on what your objective is. Do you want to actually attack someone? You want to hack your girl's phone? Okay, well, those types of hackings, you can sort of do, and there's some things that you can do that I can tell you about. It depends on what you're trying to do, though. If you're trying to break into the phone that's password protected, you might have a hard time with that. It might be just a little bit of a hard time getting that to work. How can I hack my school computer? Well, why do you want to? What's the reason behind it? Is it Chromebook Samsung to play games? Oh, do you want to play games with it? Just to snooze. Got it. Okay. Well, if you want, maybe that's something that we could go over. Maybe later. Right now, the goal for today's stream, we want to walk through Neva's AI code. So we've all week, for about a week, we've been working on having AI do click prediction for us. Neva actually got it to work. So you can actually see it does a pretty good job at clicking See the magenta circle is where the AI thinks we're going to click. The green circle is where I actually clicked. So I call this win. I call it a win. Let's see. Oh, yep. SSH server on, and then you can do hacks. Yeah, you could do that. That would be the way to do it. You can make that happen. All right, let's walk through your code, Neva. All right, so we've got a lot. All right, so we don't need to do the debugging code. We don't need to worry about those classes. We already have the draw. That's exactly the way it was before. We've got our heat map, which, right, inspired by Savan, right? Thank you, Savan. Hey, Sam, the Pokemon. The Pokemon? Your name, man. You don't know the password? Yeah, see, that's the thing. Could sworn you see in a podcast before. You know what? I've been in podcasts. Or in an interview of some sort. I've done those. So I've done Rust programming language podcasts, business-oriented podcasts, software engineering podcasts, a whole bunch of them. So maybe it's possible you might have done it, and you never know. All right, so let's see here. It would be realistic. Hey, you got a skip net. Look at that. I don't know what you're doing to the skip net. That's kind of neat. Stage 1, stage 2, concat dimensions. Yep. Okay. Ahead. Oh, you were talking about this in Discord. You're talking about this in Discord. Email Steven when you can. Well, what even would be your email? Frankie Morals. Frankie Morals. What even would be your email? Channel. Go to channel. Let's see here. More. Yeah. See, I don't have any way to email you. Oh, you know what you could do? Here's even better. Join Discord and send me a direct message. That's even better. Join the Discord and send me a direct message. That works out for me. That'll be a good way to do it. Okay. So forward, block 1, block 2. Concatenate the H1, H2, and X. Interesting. Self.head. What's this? I'm reading some oh, got it. Okay, so it's just a simple linear pass through. Okay. Concat dimensions looks good. Okay. We don't need to read that because it's not actually. Okay, so we've got a different skip net. What's that? You don't know what? Wait, you don't know what Discord is? What? So here, go. I'll show you. Go to, let's see, Stephen LB. It's right here. There's a link right here. Discord.ggxr, a whole bunch of letters. You click that, and then you find me and you send me a direct message and you're good to go. And then you're good to go. Okay. Let me get on that. I can document my own code, probably. Better idea. Yep, there you go. Hey, Taya. Hey, how's it going? Good to see you. We are today walking through Neva's artificial intelligent system that was written for click predictions. It does a very good job. Look at this. See that magenta dot, and all the green dots are where I'm clicking? The magenta dot follows. It's pretty good. I like it. That's very satisfying. It's very satisfying. That's neat. Okay, let's keep going. Okay, let's walk through it. Okay. Super init, standard stuff. Input dimensions mod 2. So if it's X, right, it needs to be, this is great. That's a neat assertion. Did you put that in there on purpose for like, that's actually pretty neat. It needs to be even, right? It needs to be even numbered. So that's why you're saying, I'm actually kind of curious. I've never used this pattern in Python before. I want to try it out. Hey, Ghost Wolf. I just noticed the live transcript on the screen. Yeah, that the one you made your on screen. This is the software that I wrote myself. Yeah, this is the software I made 7 years ago. Isn't that amazing? Love from Bangladesh, Taya. Thank you. Hello from Bangladesh. I'm over here in United States, Seattle, Washington. I'm installing Discord now. Nice. Yes, although the AI made it before I could say it should. Oh, got it. Okay. Yeah, see, I'm not used to this pattern. I want to test it out really quick. So let's go to this Python, and we'll say assert false. How do we do this? 3, assert false, comma, interesting, comma, it broke. Okay, let's try that. Assertion error. So then we say assert true. And then it didn't break. Okay. That is pretty neat. That is pretty neat because it's sort of like it requires. I don't know if I necessarily like that pattern because that's more of a rust pattern. And then how do you catch it? You have to run. It mandates. Here's the problem. It's okay for this scenario because the model really can't run unless you're giving it the correct data format, which is totally fine. I completely get it. So I think it's actually the perfect use case for an assert. However, if there's an assert in a pattern that requires the developer who's using the class implementation, the instance of it, running on it, then I think that's a problem. Hey, Rhetorus. Hey, how's it going, Rhetorus? Thank you for following. Welcome on in. Good to see you. Defensive programming using assertions. They are also common in automated testing. I love it, yeah. I love using them in test-driven development. Nice. Very nice. Very nice. Quantified Quantum, how's it going? Yep, it's the Earth's and mine too. Yep, Earth birthday. That was a really delayed comment. That was very delayed. That was very delayed. In Rust would be a panic. Yeah, so you could do panic. What is it? There is accept. Or no, I forgot what it was called. Yeah, I think it's called, maybe it is panic. I like the pattern of the result or error in Rust. I'm pretty satisfied. Result error in Rust, which is very satisfying. It makes a lot of sense. It's an easy to develop, and then you can match on it. And they've got a whole bunch of different ways to deal with that pattern. So you don't need to try accept. However, if you assert for everything like this, then I think the problem is you're causing it a problem downstream for the user to always have to use a try accept pattern, which is extra syntax, and it's pretty rough. Rhetorus, yeah, yo, Happy New Year, Rhetorus. Thank you for following. Great to have you here. We're looking at click prediction tracking here, which Neva has written for us, and we are walking through the source code, and we're going to read it, and that's what we're currently doing. We're walking through it now. All right. Input dimensions, that needs, when you're initializing the skip net. Okay, that sounds fine. Step, so, all right, every 2, mandatory 2, yep. Time steps, sounds good. This should also work, right? So since it's even, that should work as well. Though I like how you did this. I like the double /. You don't, that makes sense there. Let's see, there we go. Yes, it's not recommended for writing framework style or reusable components. Yeah, exactly. Because then you're putting all this burden on the end user of your, in this case, like your skipnet module, right? If you're the class for skipnet. However, this is perfectly fine because of, it's a mandatory thing. So I think that's fine. A result error is satisfying. I had to rehabilitate it out of your other language encoding. I know exactly. Yeah. It's just so different, the pattern, and you get used to it after a while. You do, you really do. Yeah. If you have a good compiler, errors as values is so nice. Yeah, it is, isn't it? Yeah, exactly with Rust. Okay, let's keep going. So what is this? Torch, arrange, self timestamp slow. Okay. Cache, sine, cosine for exactly our length. What are you doing here? This is interesting. So is this some sort of mechanism that you're using to capture order, like time series? Is this what this is for? I'm not familiar. I know what this is. This is essentially going to draw a circle. I mean, you can get a circle. I know you could draw a circle using this. Oh, and then you register some buffers. Nice. Very nice. So you can use those in the graph successfully without having to break anything. I like it. Similar to transformers, this is time encoding. Got it, time encoding. So it is. You are capturing the essence or the essentially the order of things. I'm actually kind of curious. What are your input demins? What did you set it to? What did you set it to? Here, I actually got a better idea. Let's go to skip net. You set it to input length. What is this? How big is input length? 8. Okay. Got it. All right. Nice. Very nice. Okay. There we go. Looking good. Okay. Let's jump back over. Where'd that go? Where was that at? Let's go back up. Okay. Let's keep on going. Let's keep it going. So I'm making this tea out of roasted date seed. That sounds like it'd be very scrumptious. That would be very scrumptious. I'm giving this to the a convolutional neural network so it has a good idea of periods. Very nice. Very nice. Thank you for walking through this. This is really exciting. We're learning a lot right now. A lot of the patterns humans do are cycles. They are circles. Yeah, they are circles, aren't they? Hey, Kyle, how's it going? Hola, ¿cómo estás? Good to see you. We are muy bien. We are muy bien. Hola. Hola. Okay, so you're using this to sort of represent time series. And here's our convolutional neural network. Your Conv 1D. Hey, wait a second, Neva. I remember you mentioning Conv 2D was required, and you got a Conv 1D there. I'm like, hey, I wonder if we could use a Conv 1D here. I was wondering. And you said, like, no, it's got to be. All right. And then what's the 4 about? So let's read this really quick. This is, so you got batch. Is this batch size right here? Kernel size, which I do believe is the window size, which should be 3 by 3 as I understand it. Yeah, you were right. Oh, really? I mean, I didn't know though. That's the thing. I'm just like, I think maybe. I was guessing. It was a complete guess. I'm like, hey, I think maybe we could use a Conv 1D here because, right? It's not, we're essentially flattening it anyways. So it might as well make it a Conv 1D because the input is going to be 1D. You specifically undo it back to the old way? Got it. You were thinking giving it space would be a smart with that one hot encoding we talked about. Yeah, the one hot encoding. That was still fun. I still think we could make that work as well if we kept going on it. Let's keep going here. Let's keep going. Okay. What is 4? I want to look that up really quick. So I want to Google this really quick. 1 second. Let's go. Wait, actually, let's do this here. I want to copy and paste this here. Copy. And then we go here. Go there. Let's see what it says. Yo, SAQ 3000, how's it going? Good to see ya. Welcome on in. Happy New Year. Happy New Year. It's good to see ya. So Conv 1D is essentially processing and predicting sequence to point. It seems like it, right? It seems like it. In channels. Hold on a second. I want to understand what this is here. So 16 input channels. Oh, 16 input channels. Okay, output channels. Kernel size. 3. I know 3 is a good industry standard. They say 3 is good. Anything less or more is different. Hey, Rhetorus. Hey, Rhetorus. Also, thank you for subscribing here on YouTube as well. Thank you for subscribing on YouTube. Good to have you here. If you didn't know, for everyone who's joining in, a lot of you already know all this, so I'm just going to repeat it again for folks who don't know. I'm Stephen Blum, CTO at PubNub. We are a big messaging infrastructure, globally distributed around the world. We have over 1 billion devices connected on our network with 68 patents, specifically around very fast, light speed messaging infrastructure for on-demand delivery, food order, multiplayer games, chat experiences, anything, IoT, when you press the button to turn the light on and off. 1 billion. All right, Kyle, thank you. Thank you for the hearts, you guys. I know it's a lot of devices that are connected to us. We're the biggest in the world. And we've got, if you've used a smart TV, if you got a phone, you've already used my technology. You've already used it. Gemini, thank you for the hearts, you guys. Floaty heart icons. Thank you. Location-based signaling. It is, right? It's location-based signaling. And we power that so that way it makes it really easy for you to drop in our SDKs. And I started the company and I'm the CTO. It's good to have you here. I'm really excited. What we do on this channel is we focus on software engineering, writing code as much from scratch as we can. Obviously, the world's changing with generative coding. I use generative coding all the time. And in order to maintain my skills so we don't atrophy, I do all coding on stream as much as possible by hand without the AI. Without the AI. We do ask the AI questions from time to time. Like right here, we're asking Gemini, like, what is this in channels? Which is basically reading the docs. So that's what we're doing. Nice. Wait, does PubNub serve push notifications? Yes, it does. We do. Yep. We do all the push notifications as well because it comes in part of it, right? We have in-app messaging, which is very fast, lightweight, light speed signaling. Additionally, we have we don't do just messaging. We do a lot more. We have a lot more on our platform, like a bunch of stuff. audience engagement, collaboration, IoT workflows, dispatch, geolocation, event-driven architecture, operations, gamification, moderation, a whole bunch of things. It's just a lot of stuff. And we give this, we sell the platform, essentially. It's like, you want to use the technology? We've got a messaging infrastructure and a whole bunch of other services as well. Yeah, this is my company. It's good to have you here. So, Stephen, I found the time dilation is happening not because of traveling fast in space, but because of bending fabric of space itself. SAQ 3000. Hey, Gunhighs, good to see you. Let's go. Yes, let's go. Exactly. Good to have you here. We're reviewing today's goal of the stream is we are reviewing Neva's code that got our click predictor to actually work. Look how good it is now. See that magenta dot where I'm clicking? The magenta dot is very, very close. Essentially good enough. It's predicting the future. It predicts the future. It's so good. Let's let everyone's wishes become real. I know, right? Hey, that's a great idea. That sounds like a good idea to me. Yeah, you're new to Python? Wait, sorry, I missed your message. Let's see here. I saw a message earlier. You said something about being new to Python. Where was that at? Oh, you're new to Python and this content looks encouraging. Hey, perfect channel for that. Yeah, I like Python. I like AI. We're doing Pytorch and AI. That is a big part of it. We also do Rust. We could do C#. We could do any language, right? We can basically I've used almost every language. I like them all. Rust is my favorite. JavaScript also big one in there. So many different languages, you guys. Happy New Year. Anyway, Happy New Year, Stephen. Thank you. Wish you the best for the 2026. Love you. Thank you. You too. You too. Have a great New Year. Have a great New Year, you guys. So let's keep going on the code here. Hey, Reaction HG, you subscribed? Hey, there we go. Thank you for your subscription. You're a pen tester. All right, penetration testing. And you write your own exploits. I do use AI sometimes to write them. Yeah, there you go. You are on the right track. That level of security is going to be more necessary than ever. All these AI code generators are out there being used by a lot of people who don't check for security in their application before they deploy it on the internet, right? We want to be a little careful. You got to be a little careful there. They're not careful. So, Reaction HG, we need you to continue your penetration testings. Thank you for doing that. You're doing it right. Stephen, remember when I said I was selling computers? I just got a new one from my sales. Hey, very nice. Would you, cough, not me. Oh, really? Yeah. Well, I hope it was good. Curious about that time dilation stuff. It was very simple explanation. Nice. Is that time space? I like the time space channel or space time. It's called space time. I like the space time channel. Let's see. I'm actually kind of curious. Is that the space time channel? We're double checking here.
You probably...
No, that's float head physics. Okay. That's also a good one. Nice. RTX 3050, 32 gigs of RAM and 1 terabyte SSD. Ooh. Hey, that's a beefy one. Okay. Quantum is going to be a game changer. It really is. It's completely different. I'm excited for it. I'm excited for Quantum. Okay, let's keep going. All right, so we've got our time series, or sort of time encoding with each click. And I really want to see where this is going to be. I want to see how the math works here. Okay. So B is the shape. Okay. Forward, B shape. So X, batch, and then D is equal to the input dimensions. Okay. So of course you want the batch. Got it. Makes sense. Reshape B, T for time steps. Okay. View sequences. Nice. I'm actually kind of curious to see what that looks like. I'd really like to see what that looks like. I mean, I can visualize it here. I know it's a 3D matrix. Essentially, though, batch, we don't care about the batch. We only care about this. So step dimensions is, what is this? Is this 2? Is it 2? I think it was 2, right? It is 2, yes. Okay. All right. And then time steps is going to be 1. Is it 1 based on the math? Yeah, it's 1. So that's weird. That's very weird. See how that works there. No, it's floating head physics channel. I haven't heard about, and you saw that it was very simple explanation and fast. Nice. Very nice SAQ 3000. I like simple explanations. They're my favorite. Okay, let's keep going. Let's keep looking at the code here. Okay, so this will, let's go over here. Let's go click that button there. Okay. Steven, time steps would be 8 there and are 8 inputs. Oh, really? Okay. Because step dimensions, I was reading through this, and step dimensions I do believe is currently 2. Time steps is input dimensions. Oh, got it. And then input dimensions is going to be 8. I saw it. I saw it was 8. So time steps will be 4. So you've got 2 and 4. Got it. 2 and 4. Okay. So it'll be 2 and 4. So it's this very simple 2x4 matrix. Very simple 2x4 matrix. And the batch size, right? I'm pretty sure. Okay, let's keep going here. So then we use the registered buffers. Expand. So I'm not familiar with this. I do not necessarily understand what this looks like. I would very much like to print it out though. So here's what I want to do. I want to rerun this code and print it at various locations so you can see kind of what it looks like. Although it is kind of being represented here, so you can kind of see that it's being represented there, right? V, there we go. Yeah, you can see all the dimensions here. And then you concatenate. So you add these all together. Really? This is neat. This line right here. I love it. This is, so you don't have a separate encoding anymore. You did not separate out the encoding. You just put it all in the forward function. This is all in the forward function. Skip net forward. Okay. So essentially this is you encoding. This is you're encoding it right here. China programmers are actually getting good. They're very good. They're absolutely very good. Hey, how's it going? Sir Trigger Oscar. How's it going? I'm pretty good at coding, but still need a mentor. Can you please help? Sure. Any questions you want to know? Anything you want to know? I'm happy to help. So I'm, if you don't know who I am, Stephen Blum, CTO at PubNub, globally distributed infrastructure, running on AWS in all the regions for messaging, built-in app messaging. We have already 1 billion devices connected and many patents. Many patents. Any questions you have, I'll be happy to tell all you the things that worked for me over the years. So if you have any questions, let me know. That's what we're here for. We're here for you guys. We're here for you guys. We're here for you. Did anyone hear that Russia, America, and etc. want to build nuclear power plants on the moon? Well, that's the only way. Although I think we'll have a problem with cooling. I think there'll be a challenge with cooling. We'll need to like, we'll need new technology or a way to generate water on the moon of some sort. I met someone, a young Indian programmer that are cooking. There are some talented people in the world. You got it. Did Elon give up on Mars? I think Elon's still working on that. Still actively working on it. Okay, so this right here, Neva, is my favorite line. I see what this looks like and it is very satisfying. So you're essentially adding all of the inputs. So where's X at? X, you change the view to be based on this new shape. And then you have, where's that at? Sequence. Self, unsqueeze, expand based on the batches. Okay. So you could have, this is, you don't necessarily need to do this every single, right? This could have been cached. We could have cached this. This could be cached right here. How's it going? Lobeto, how's it going, Lobeto? Thank you for subscribing. Welcome on in. Good to see you. Happy New Year. Happy New Year. We are happy to have you here. We're currently working on Neva's code walkthrough, who wrote a click predictor that works very well. As you can see here, here's the click predictor. You can see, oh, it's very satisfying. Oh, it looks so good. Oh, isn't that great? Wow. That's stunning. That is absolutely stunning. For deaf people, cash me outside. What? That's a crazy boon, Quantum. Is it? Oh, and Russia are going to make nuclear power plants on the moon. I mean, it's the only way, other than like solar. Solar would be great, I think. Although solar would degrade very quickly because you've got a lot of unprotected radiation. So your panels would degrade quickly. The reason why nuclear is great because it's a self-contained power source that you can operate for many years. So I think that's why nuclear is the only option. We're officially 2023 cooked. Cooked like rice. Cooked like rice. It could be, but since it's just a way you view it and not actually data, it should be basically free. Got it. Okay. Yeah. I'm just over optimizing here. I'm walking through. I'm like, this is me in my process of understanding the code. Okay, so this line is my favorite, line 341. I love this line. This is great. It's stunning. It's absolutely stunning. So you take the results of your sine, cosine, and then you pop them in over here to concatenate on the sequence itself, which is pretty neat. Although, let me see here. Cached. Since this is, it is odd though. I'm kind of curious because wouldn't this be a constant for all of our inputs? Wouldn't this be constant for all of it? So this would always look like the same on the tail end, right? Because concatenate will just append to the array. And so I'm curious about this because I thought the cosine would be sort of manipulated a little bit differently. So I'm curious how that works. Solar system debris too. Yeah, exactly. Nuclear is better than oil and coal. Also, solar and it's better, but the problem is with capacity. Yeah, we need to store the power for when electricity is not produced by them. So by being, yeah, okay, that makes sense. Nuclear is always on, which we rather do code reviews. I know, rarely do code reviews. I'm having a lot of fun with this. Skynet on the moon. Oh, yeah, Skynet on the moon. 1 hour to go for New Year. Other work. Hey, it's almost New Year, almost 2026 for you. For me, it's quite a while away. Although, technically, we're all on the same planet, going around in the same spot, right? So it should be New Year everywhere, all at the same time, I think. It's an artificial human construct that we're doing it this way. It would be constant, yes, but look what it's passed to. It's a convnet. Okay. SAQ. All right, so B times step. So yeah, a constant there. Okay, so this is a constant. So you got this sequence, and then you permute that. Okay. And then you put it through a conv. On your conv is going to be. Let me see what that looks here. I've got an idea. Let's bring this up here so I can see it better. Okay, here you go. Oh, you even have dropout. Interesting. I didn't know that you would add dropout. That's neat. Might as well. Kernel size, padding. Okay, so this is it going to be the same? So far, all this is the same. This to me looks like it's constant so far. Like everything calculated up to this point is always going to be the same for every input. Tell me I'm wrong. Tell me I'm wrong. I'm reading this. I'm like thinking this is always going to be identical every single time. It's always the same. Pretty sure, unless you know the different batch sizes, I believe, because you've got a different batch shape there. Genetic testing with AI on the moon. Moonlings? Maybe. We could, right? So that would be a way to get around all of the, I guess, what do you call it? Laws? Like the laws and like legal requirements? The input X is different. So, wait, did we, X. Oh, I got it right here. Okay. I missed that. Okay, thank you. I missed this. So we're actually using the X data and we're putting over a view with the time step and dimensions. Okay. So we're changing the X. Okay, got it. Thank you. Thank you, Neva. You corrected me. I see it now. I see it right here. So it's always going to be different. Every single input, wherever the click is going to be, it will be different. Okay. There. That's the key. That's the key. All right. I'm happy about that. I like it. I like it. Okay. Then we do a reshaping, which makes it into, it looks like a single dimension array. Is that what that does? It reshapes into a single dimension, one-dimensional array. Then you project onto the flat, which is interesting. So a lot of this, like I've never done this kind of, I've never used these specific functions before. Usually when I'm trying to manipulate whatever the input's going to be. I do this all by hand. And all of these main functions do this slightly differently than I would do it. Just slightly differently. I read the article on symbolic AI, very aligned with some of your ideas, seeing that the formulas really helped. Great to hear. Great to hear. Yes, from 2D to 1D. Yeah, all right, we're figuring this out. Time to vanish, quantify quantum. All right, great to see you. Thank you for stopping in. Happy New Year. Happy New Year. We're going to keep going here. We're going to keep going. Okay. So self.head, which is what is this for? Head. Where is that at? Okay, here we go. Oh, a linear. Okay, so it's a linear with the concatenated dimensions, projected dimensions. Okay. Where's this at? Where is that defined? Oh, 128. Whoa. That's interesting. Okay. Interesting. Okay. I want to see... So what I want to do now is I want to start stepping through some of this. Let's keep reading. And then we'll start printing out some of the things I want to see. Okay, so all that's the same as before. Input dimensions looks good. SkipNet, we got the SkipNet model. All right, that's pretty neat. I like that. All right, so instead of putting our model directly defined inside of this NN predictor, we set it up here. We put it up here. And now this has all of the things here. And then also has a forward separate from the predictor. But are you going to also have a forward in this, though? I think you will. Okay, so you just got it. Okay, yeah, it's just a pass-through. Okay, that makes sense. Just a pass-through there. Okay. Looks good. Same optimizer as before. Tracking the losses. Append the losses. And then, let me see here. Losses that detach. Append. Backward. Losses. Sum. All right, so this is the cost. All right, so we're doing the cost here. And then we print the cost. Okay, great. Sounds good to me. Yes, you missed the reason it's called SkipNet. In the input, it's also directly given to the linear head. SkipNet. Skip. Okay. Why would we call it SkipNet? That's actually good. I just thought it was a fancy word. I just thought it was fancy. I liked it. I really like that it's called SkipNet. Let's see. I don't know why. Why would we call it SkipNet? I feel like I should be able to figure it out. I haven't yet though. Let's see, keep going. Compile. Optimizer looks good. Max samples. Training data size. All right, sounds good. All the same as before. Okay. Looks good. To device. Self. The entire self. Wait, what? You can do that? Wait, no way. So everything can go to device. You can do that? That is neat. I didn't know you could do that. Okay, I had it the other layers before. I think I removed that because it was good this way. Anyway, okay. It says skip in the comment. There's a cat which makes it there. Okay. Cat. Let's see here. Cat. I'm gonna look through it. Cat, concatenate. Where is that at? Head uses original input plus a convolutional projection. There is a cat here. Add cached. Wait, what? Okay. Comp expects. Skip cat concat. Wait, what do you mean skip concat? That doesn't look like it's skipping. That doesn't look skipping to me. It looks like it's straight up concatenating. What? Hold on a second. Skip concat, original plus com features. H, project, flat, sequence. Okay. So here's your fun projection of the X. And then you also, so you keep X originally, and then you also add in the H. That's interesting. That is interesting. Wait, H comma X, or it's skip concat. It's a straight up concat. Like I still don't get it. Okay, La la la. All right, let's keep going. All right, what I want to do next is all the code is basically the same at this point. This looks different. Buffer management. Append the sample. Different but similar. What is this? All right, what is fit recent? Oh, whoops, no, we want control WS. There we go. All right, skip recent. Fit recent. What is this? La la. Came in. These, all right, gotta go see it. All right, SAQ 3000, Happy New Year. Good to have you here. We'll see you next year. Or a little bit later. These are the calls I recognize from running large language models on local devices. I realize I basically know the torch parts in running large language models and tuning hyperparameters. Nice, Savon, nice. Symbolic AI uses human-coded rules and logic like if-then. Modern large language models use deep learning neural networks. They try to mimic neurons with nodes, basically. So I am curious about the symbolic AI and how that is going to be progressing. AI science. I'm curious about it. They lack inherent interpretations. They do. All right, so I'm curious about fit recent. Let's check this out. Training data set size, account, features, self, float, torch, tensor, label, flow, sample count. Okay. Features and labels. All right. So we're creating our X and Y. Model.train. Oh, fit. This is the train function. Okay. So, got it. This is our train function here. So earlier we had this train method, or did we? Let's see here. 1 second. Is it around here somewhere? Self. Oh, wait. Def train. It's not there anymore. Okay. So that is using Pytorch directly. They rely on statistical correlation. Graph rags is interesting implementation. Okay. The more we know, you guys. The more we know. All right. I'm curious about gradient noise. There's a lot going on here. There's a lot. I feel like this is a little bit more. If Nan or Infinity kill it. Yes. Yeah. This is like exploding or vanishing problems. Or division by 0. This is you really hope to never have to deal with this. Okay. All right. Fit recent. This is the train function, so we're getting our X and Y inputs. Although immediately it just says self.model.train, which is weird. So what is X and Y used for here? And this, Neva, this is where you started defining functions inside of functions. So it was like, hey, I saw you doing this earlier. You're like, you've got a def fit recent right here, def fit recent. And then right down here, you've got, isn't that amazing? Right here, you've got, see, you got two things defined at once. You get a def up top and a def inside. You're laying your definitions, which is a pattern that I used to use. I like doing that if I can make my def small enough to do it. Also, you use it for lexical scoping. So I completely understand why you would do something like this as well, because then you can leverage access to variables in the previous scope. So I get it. I understand. It's an easy way to do that. Functional programming. Understood. Yeah. So it's a result of cost being the res, because for inputs close to 0, it's going to be division by 0 or close to it. Got it. Okay. Understood. It's unfortunate that has to happen, because I feel like we can sort of keep track of all the values and the parameters, so that way they don't fully hit potential infinities or not a numbers. I feel like you got to run. All right, Savan, we'll try to catch the stream in a bit. All right, Happy New Year. Sounds good. Thank you, Savan. Hey, Steve, how's it going? Steve Maloney. Thanks for making this fun, Steven. Yeah, you're absolutely happy to do it. This is a strategic topic often. I'm enjoying this. So TensorFlow and Pytorch and Python, that's what we're going through right now. We're going through all this stuff. Right now we're going through Neva's version of the click tracker, which does a very good job. It does a very good job, like very satisfying. So you can see how well it performs. You can see where I'm clicking and see the magenta circle. Beautiful. Beautiful. It's basically exactly what I was looking for. So it's fantastic. Hey, Longcross, how's it going? Happy New Year. Happy New Year. Thank you for jumping in and stopping on by. Good to have you here. Good to have you. All right, so let's keep going. Let's keep walking through this code. All right, so where's X and Y being used? K, X, and Y. So K's here, okay. So you're getting your features and labels. Straightforward. But then you say model.train here, which is what? Let me see here. No, that's within the class. All right. Then you've got these sort of like internal hidden functions that you're going to access later, which I assume you're going to say weighted loss insight. Yep, right there. Okay. Weighted loss. Torch. Shifts. Okay. Normalize. ABS. Clamp. So, see, right here, if you're clamping, I mean, can't we see? This is like also like I was wondering if we could like instead of like allowing things to hit 0 or get too large, I feel like we could do some sort of clamping or something like that tapers, like a normalization function or something. Obviously, like maybe an expanded version of like 10H or something. Train is a built-in for Pytorch. It moves it to training mode. Oh, right. I forgot. Okay. Thank you, Neva. I forgot about that. Right. All right. So it moves it to training mode. So it doesn't actually train the model. It just moves it to training mode, which sets it up in a way that it allows things like this, right? The dropout. It allows the dropout layers to be active. And if you disable training mode, dropout no longer is being used in the feed forward neural network. So that's like, for example, right? During the training. So I remember, I know that much. Yeah, clamping here solves it. It shouldn't even be needed, but it's weird for weird bugs. Understood. That makes sense. The assert is for making sure that if I rewrite the cost badly, it yells at you. Ah, nice. Okay. Got it. Okay. So it's like a nice little protection there for you as you're manipulating and changing the different algorithms and the loss function, for example, things like that, and the cost. No worries. All good. That makes a lot of sense. Thank you, Neva. That describes it. Okay, so train. Here we go. Train, but like that. All right, there we go. Okay. So now you've got a shifting learning rate. So at the beginning, it starts off extra, and then you slow it down by 1 factor of magnitude. Sounds good. Also note, it adds random noise to the gradient to keep the model loose. I saw that. I saw you did noise. Noise. Add gradient noise. I saw this. And does it add a lot or a little? Oh, this also does checking here. So for all the parameters, if there is no gradient, you only do it to the gradient. So during the training process. Okay, that's interesting. I've never used that strategy before. That is pretty neat. So when the model is learning, you slightly shift the parameters. Let's keep going. G gradient. So you got the gradient. It's very moderate. I'm curious. I want to look at it. So here's the noise, and then you're adding the noise. Couldn't you do like G plus noise? Oh, wait. G equals G plus noise. Because it's Pytorch, right? It's kind of like, should this be able to work? I'm pretty sure. Or you can't do that because p.grad. So you'd have to say p.grad. P.grad equals p plus equals, right? You could do something like that, plus equals noise. I'm just wondering if that's also possible. No, because normal plus keeps gradient. Got it. Okay. Add will make it it permanently, so it's a mutation. You see the underscore methods used for gradients and parameters a lot. Really? Okay. All right. Like it might be fine. Actually, not sure. Okay, got it. Understood. I got it. Understood. I was kind of curious. Okay, so noise random. All right, so you get a random G, multiply it by 2, and then multiply it STD. What is STD? So let's see. Uniform. Okay. What is? I'm curious about what STD is. Is it a? It should be a very small number, right? I'm assuming. I'm assuming it's a small number to keep the noise pretty beefy or pretty lightweight. So let's see. WS. Let me search this. Oh, it's up here. It is a very small number. All right. It's almost like an epsilon at that point. It's very small. All right. Very happy with that. Very happy with that. Okay. So you add a very, very small amount of noise to the gradient. That is neat. That is very neat. I did not know that you could do that. It makes a lot of sense. And also, yeah, okay. Wait, this is weird. I mean, I feel like there's some counterintuitive action going on here. Torch with no gradient. Then you use the gradient right here. Like, you're straight up using the gradient right here. Like, what's going on? With no gradient, but actually, just kidding. We're actually using the gradient right here. What? That's so weird. Like it might be, it's 10% of the smallest learning, right? So it's not too tiny. Got it. All right. So it's a little bit tiny, but not too tiny. Hey, Savon, you're back. You're waiting for Neva's README, as I need to catch up on some Torch stuff fully to understand the code. Me too, a bit. There's a lot of things in here that I tend to do manually that Pytorch comes pre-built with all those algorithms. So you can do a lot of like easier math operations, like the permute and the reshape. I get concat, that's a straightforward one. And you got this project. What's the difference between, these projects and other things? Like, these are things that I want to practice myself. Otherwise, I end up doing it manually. And I'd rather use the framework to do those things. He needs to generate noise. I know, you got to generate some noise. Just a smidge noise just to make things exciting. Keep on some noise from the excitement. Is it actually necessary in the code I showed you? Is it? It's actually necessary. You got to generate the noise. It's mandatory. There's no reason why you should ever not have the noise. Okay. All right, so I'm happy with that. So here's where we added the gradient noise. And then we do the standard other stuff. All right, looks good. Looks good to me. Say, no, you, redo, undo. Okay, there we go. Okay, so are we still in our fit? Okay, so you're training here. I don't know what this is about. Obviously, okay, so you are phase 2. What are we doing in phase 2? Oh, you're training it with different approaches. You've got multi-phase training. All right. I've not ever needed to do this before, but you can make it. How's it going there? Annie, hey, are you guys hiring? Yes, we are. We are hiring. Annie X, we are absolutely hiring. I'll show you here in a second. Cut the input, only the last 8 samples. Got it. All right, so you're only going to grab the last 8 samples, and then you're going to continue on with a slightly different training approach, or is it identical? Is it exactly the same, or is it different? Full train for all the data, and then you only do a little bit of the data. So then you optimize for the most recent. Is that what that is? You're optimizing for the most recent? I'm guessing. This is my assumption. Yeah, all right. So, Annie, yes, we are hiring. I'll show you here. We do have some roles. If you go to PubNub Careers, and click on the button, and you see at the bottom we got a couple of open roles here. We got a couple of open roles. Yep, some of you have already applied, and you'll be competing. I did most very classical machine learning in my past, so opposite to deep learning from scratch. Hey, well, they're very similar. I mean, you just add more layers, right? That's the only thing. I need to fill on some NN and machine learning to understand. I mostly use transformers and Hugging Face abstractions. Existing models, so much new models creations apart from using support vector machines, right? And naive bias. Nice. The decay is more aggressive and it keeps with the same cosine learning rate. Oh, okay. Optimizer learning rate, PG, okay. Let's see here. We're making, I'm getting a little bit, I'm seeing here. Okay, got it. So a little bit heavier here. I see this. So like the difference between this and this right here. So you got the difference there. So you got two different differences there. You see on the screen. 50%, or it's double essentially on the second phase. On the loss. So you increase the weighted loss. What is our weighted loss again? Our weighted loss looks like this here. Let's look through this. All right, right. Okay, we read through this earlier. X shift, average, normalize. Okay. All right. And this is right. This is the function that's inside your other functions. Okay. Looks good to me. All right. Update predictor. All right. That's just normal stuff, I think, from there. Although this looks different. Build only new training window. This is like just a complete shift away from what we were doing earlier. So it's kind of neat to walk through it to see what you've done. Essentially, you rewrote the whole thing, other than the visualization. That's it. You rewrote it all, Neva. You wrote it all. It's kind of crazy. All right. So unified AI pipeline, update predictor, input coordinates. Fit recent. Okay. Least predict newest. Optimization on what you had earlier, otherwise the same. Yeah, I would say it's an optimization. Like just a little bit of an optimization. Like it's like a full new model and a whole new approach with various optimizations. It's pretty great and it works really well. You can see the result. It's fantastic. I really like to see this. This is great. It works very well. For the most part, it works very well. Coordinates. Okay, so now we're just doing the regular prediction. And then the rest. See, this part right here. That's all the same right there. That's only like 100 lines of code. You added like 500 lines of code. You made a whole. Well, I mean, a lot of it's double. So like you've got a whole section here like that's commented out. Did you use AI to improve it? No, like that function is exactly the old version of how you gathered input. Yeah, it is. Yep. But I'm not making a new array every time. Got it. Okay. Yeah, sounds good. This is my vibe coding, isn't it? It looks, the way I'm reading this, it looks like it's a lot of manual, a lot of manual stuff. This might be a little AI-ish. This looks a little AI-ish. Although some of the things in here look like Neva wrote. It kind of reminds me of Gemini. Like if I'm looking through this, I feel like this is it's like this doesn't necessarily look like a Claude code output. If it was AI generated, it does look like some manual or the use of Gemini or Codex maybe, not Claude. Although I could be wrong. As Claude is usually more flowery. I never take the first input. Ask it again. It's GPT-5. Got it. Okay, so Codex. Nice. Always ask again. Keep on asking. Happy New Year's, Fractal Cow. Good to see ya. Thank you for the likes, you guys. Thank you for liking the stream. Little floaty heart icons there. Fractal Cow, Happy New Year. Good to see ya. Hey, rank it upon up now. Rank it up now. Rank it up now. How's it going? Good to see ya. No, just chat client. Nice. Okay. Codex is too too slow. So you do copy and paste, Yeah, codecs definitely takes its time. It's good to have you guys here. Happy New Year. Welcome on in. We're walking through Neva's source code that completely changed how we did our click prediction. And this will conclude our click prediction series. And I'm very excited about it. What I want to do is maybe continue reading here a little bit more and then look to see if we can find some of the outputs. I'm kind of curious about what they look like. I kind of just want to get the feel for it. Working with all the AIs, you get used to their code and comment style. You do, right? You do, yeah. Like Claude is very verbose, flowery, warm, fuzzy, sort of like tones of like, I don't know, like I guess a wood tone. And then you get something like Gemini, which is very precise, concise, short. It gets the job done quick, very fast. And then you look at Codex, and it's more like a laser beam. It looks like a laser beam. It's like a different kind of approach. Okay, let's keep going. All right. I think we basically walked through everything because all that's the same for the most part. Yeah. Okay, so only every 7 frames. Yep, so it's basically all the same as it was before. Oh, well, sort of. Well, click, previous marker, click. Okay, position. Okay, so. Got it. Okay, so click. I'm just double checking this here. Click, click. Previous click. Okay, great. Okay. So that's all the same. All right, walk through it. Neva, this was fantastic. Thank you for doing this. You made a fantastic outcome. It works very well, very satisfied with it. And you taught us a lot of things today. And it's very neat. README is up on GitHub for the branch. All right, let's pull the README. Okay, CD click. All right, git pull origin minimal vi readme. All right, let's take a look at this. Okay, let's read through it. Set wrap. All right, click prediction. This code was originally something Steven did on stream, and I had time to play with a lot. Nice. The graphics is not by me, but the prediction is. You did all the AI work. You did. I'm going to do my best to explain the thought process for what is happening. Note that this is vibe coded. Okay, it is. Okay. 5.2 chat client. I really did not mean for this to get as much attention as it did. Hey, you made it work. So you made it work. My whole process is to use minimal AI because, we want to walk through and learn it together. And so we kind of got introduced to a big torrent of a whole new things that I didn't know you could do with Pytorch. So there was still learning had by all. It was great. Thank you. You did a great job. Let's keep going. Principles. So after playing around with it, one hot encoding with the CNNs, right? I like the one hot encoding. Still fine with that. We probably could have gone further with that. I feel like it would have been still possible to train a model with that approach. I feel like we could have manipulated it a little bit in different ways. I feel like we could have done it. So we simply do not have the data to train a big model. Right. We didn't have enough data. We need more clicks. So fundamentally, we are basically trying the smallest network we can get away with. We ideally want to not require too many examples before we can start training. Makes sense to me. This naturally means that we want a convnet, a convolutional neural network, and a linear output for the regression, for the click prediction, as they work great with small amounts of parameters. Hey, there we go. Also note that this is continuous training, so we need to keep the network elastic. Okay. And now we're going to learn about elasticity. Let's go here. Let's go. All right. So let's learn about some elasticity here. After playing around with a lot of models, I noticed that they can sometimes get stuck on particular patterns. Yep, they and they like find a pattern that works and they get stuck there, and they might not learn other patterns. Sigmoid activation has a nasty tendency to have a vanishing derivative on these edges, and thus we are using no activation. I mean, I saw ReLU in there, but ReLU isn't necessarily an activation. I mean, it just sort of, it's a clipper, right? All it does, it clips at 0, right? That's all it does. So kind of an activation, but not really, which means we can predict clicks off screen, and it's worth it. Another issue is if we, at any point, 2.2 neurons have the exact same weights, they would stay the same forever. Really? I didn't know that. That sounds like a problem. This gradually leads to them being locked forever and a model effectively having one less neuron. Also, if something goes very negative into the ReLU, we get those dead neurons. Yep, because it's 0, because it stays 0, right? The derivative is 0 and it stays 0. So it's gone forever with the ReLU. Try to solve both with weights and random movement by giving small noise to the gradients, which means that takes care of the zeros. That's pretty neat. We also add dropout to encourage neurons to be different. Okay. Here we go. Skip connections. Here's the skip connections part. We're learning about the rest of what Neva wrote here. Note that a lot of the times a click is directly related to the input. So adding that to the last prediction head does wonders. It makes a lot of sense, right? We want to have a time series, right? We need to represent. Adding that to the last prediction head does wonders. In general, because we want training to adapt quickly, we want the least amount of distance between each weight and the cost. The network is aggressively optimized to be short in terms of layers. Okay, so there's not very many layers. That's something that we noticed. I saw some conv layer. I saw a linear layer. And was there anything else? Sequentials here. Yep, a conv and then a linear layer. And then one more linear layer right here. So I just saw just 3 layers. It's not a lot, right? It's not a lot. Neva, that's amazing. I think it's weird that AI is trying to imitate biology. If biology is the ultimate goal, then robots are unnecessary. Huh. If it can manipulate biology, even us humans have been very unable to manipulate, but we're okay. We can like push biology one way or another. Currently a total of 3, like that's a minimum of a, yeah, it's like the minimum. Yeah, Torva, you got it. It's the minimum. Or wait, sorry, Neva. Got it, Neva. That's the minimum for deep. It's the minimum for deep. You got it, Neva. Got it. So yeah, so you got 1 here, and then we've got basically another right here. And then we've got a third up here. So basically all these right here. 1, 2, and 3. Okay. Pretty neat. And you've got ReLU and dropout after each of them, except for the head, which would be the output. So as far as I can tell, this looks like the output to me, right? Because your output is 2 regressing X and Y coordinate. All right, let's go back to it. Originally, I had a bunch of skip connections, but it seems to work the same way either way. Some refactor got rid of the parts of it. You think it's actually nicer this way. I like simple. Simple is better. So we're using a weighted loss function that exponentially decays in time. The first part of the training uses all of it and a lower decay. So we grab all the data up front, while the last part uses only a few examples and more aggressive decay. Got it. Tried a lot. ReLU is best. Soft min, low key great. Okay, so we could have also done soft min, which I've never used soft min. I've used soft max, so I assume it's the opposite of soft max. Okay. Oh, Torva, you said, nice approach. So we have basically probability of click coordinates, random factor, results eval. Yes, you're right, Torva. Yes. I mean, it wouldn't be the ultimate robotic design, be self-regenerating and self-replicating. Yeah. There you go. Conway's game of life, self-replicating. So now we've got this beautiful click prediction. It works very well. Neva, thank you for doing this. This was great. This was really great. This did sort of bump us up to the end very quickly. And so now we're basically done with this series. Hey, what if I'm you're a slob? Global production or global? Then what do you mean? Oh, you don't, in terms of replication? Are you talking in terms of replication? I'm actually kind of curious about that. So this did bring us up to the point of, hey, we did it. Neva, thank you for this. We kind of basically wrapped this up. So we've got a click predictor that works very well. It does the job and it trains fairly quickly. And we've got it visualized. So you can see it visualized. It works very well. I'm very happy with this. This is fantastic. And now that's it. We've concluded. There's nothing left to do. I call it basically done. Can this be optimized further? Probably. Can it be simplified? I don't know. It's actually already a fairly simple model. As you can see here, there's very little in terms of the model itself. There's just a lot of manipulation on the input to the model. That's where the majority of the code is focusing on getting the data the right shape as it is entered into the model, which is the most important part, I think, right? It's a critical aspect to AI, getting the data in the right shape. Otherwise, as you can see here, very simple model. There's only 3 layers. I'd probably sit on more stuff with the architecture. It's kind of fun to work on. Is it? Nice. Well, if you do any other upgrades and modifications, we'll be happy to look over it again on stream in the future. So going forward, we do want to probably start something. We got to start a new project. What are we going to do next? It's new year, right? New year, new project. And also, Neva, if you do end up doing any modifications, I would like to revisit this and come back to it because it is a very great learning experience. Fantastic learning experience. Okay, everyone. Now, I think we did pretty good here. Let's see. We're on our way. You would like to make new robots with improvements? I kind of want to make robots. I think that would be a lot of fun. Build robots that dance. I want to build dancing robots. Okay. Technically, yes, it's possible. The perfect robot itself would not need to regenerate itself. Only adapt. It would make new robots with improvements. Hey, Steven, would make releases and DM you. When it's a good time to do a revisit, sounds good to me. Some large language model fine-tuning. Well, that's an interesting idea. What would we want to fine-tune it on, though? See, that's my question. Like, we could do fine-tuning, and it's fairly straightforward. It's just what would we want to fine-tune? I mean, we could try to add new knowledge, though that I don't know how we'd recognize the performance on that. That would be pretty neat, though. I think that would be pretty neat. Maybe we could do that. So maybe not so interesting. We need an objective. Like we need to fine tune the model. I suppose what we could do is we could try to teach it to write certain kind of code in a certain kind of way and then test it over time. That would be pretty neat. We could absolutely do that. That would be pretty neat. We could. Also, the challenge with large language model is it's expensive, right? It's a little bit expensive. We need to spin up some expensive, maybe a comp coder. It's won and helped create. What's a comp coder? Funny, the first AI reached general intelligence will most likely be language-based. It seems like it might. Because that's where all the investment's going right now. That could be a cool idea, an AI that detects skeletal structures in an image and then makes them dance. Oh, right? That would be unexpected. Why would you even, like, people will be like, what are you doing? Mostly boilerplate stuff. True, it's expensive. Yeah, it's expensive. Comcoder is a large language model. Oh, is it? It's supposed to work well in C++. Nice. Okay. So yeah, maybe we could fine-tune comcoder. Let's take a look at that really quick. Comcoder LM. Is it comp code R? Comp code R. Okay, comp code R. Is this the right one? R package 7. This looks like awesome code, comp coder. Okay. Yeah, we'll have to look. We'll have to look. So that's one of the ideas on the table. We've got large language model fine tuning, and we want like to fine tune it for some reason, right? So that means collecting the data and and getting ready for that. Gemini, of course, right? I know, right? Like, what is the best language for LM coding? Gemini, of course, because it's Google results. Why wouldn't they? And they also give some other examples in here, but I like how it goes Gemini Pro. Depends on consistently top benchmarks. Yeah. Okay, you guys. I guess we're basically done. We achieved the goal. Neva achieved the goal for us. Thank you, Neva. We read through the code. Looks good. And for next, which is New Year's, tomorrow, which is the first. For me, it'll be the first. Using Meta Ray-Bans right now. Are you? Really? No way. How is it? Is it neat? Yay, victory. All right, yay, victory. We did it. Neva, thank you. Thank you, Neva. That was fantastic. Great experience overall. All right, so I suppose what we could do is we could also look over our future stream ideas. Let's go to future stream ideas. Go through all the loss functions, build something for Kalshi, or do some more algorithmic trading. Training AI to do ASCII art. That'd be pretty neat. Look at LangChain. We could build an AI agent. TinyGrad, N8N, Llama Index. There's a lot of stuff in here. We already upgraded our subtitles, so that's a good one. They're your dad's. Oh, nice. Using the X Real Air 2 Pros. Torva, what are those? X Real Air 2 Pro. What is this? Oh, hey, there we go. Of all the best-selling AR glasses, these are in the top. This is nice. Thank you for the likes, you guys. Thank you for liking the stream. Using AI, obviously. Is it analyzing stocks and get investment recommendations using AI? Yeah, exactly. Yep, we could do that. So that was actually something else I wanted to do. We've done, day trading. Thank you for the hearts and likes, you guys. Thank you for liking the stream. It's great to have you here. You mean some quant would be fun? Yeah, I think quant would be fun. I think that might be in like a nice New Year's thing. Do some quant trading. We could do that. We absolutely could do that. And there's a lot of ideas that can go into making that possible. So there's some ideas there. There's some ideas. I like that one. And then we can use Pytorch to help us along the way. Can we make apps for this Ray-Bans? I think so, right? You totally can. You absolutely can. I assume that they want you to. Wait, is that what that looks like? Oh, what? Oh, okay. I didn't realize that there's these lenses right here. It's like you zoom in on this. Like, see how the glasses, like, I didn't know there's these extra protruding lenses. It makes sense because you need something to project onto. So, I get it. I was wondering how that worked. That's neat. And if you look at this, so you can see where the I guess the screen projection is right here. Yeah, I have the screen display in front of your eyes. Nice. Very nice. Okay. So there's a lot of ideas here. So we could also do some fundamental stuff to like just walk through if anyone's interested in the fundamentals. We can walk through that. Okay. Well, I guess we're good to go then. It was great to have everyone here. We're wrapping up now. Had a good stream. Good to have you here. And we'll be back tomorrow on New Year's Day. Should be good. Let me double check. Let's look at the clock here really quick. And then we can, let's see here, calendar, make sure we're good. And then we can get started on some new stuff. Sounds good to me. Looks good. All right, you guys. Wait, today's Wednesday? Oh, wow, time goes by fast, doesn't it? That's amazing. Good fun hanging out here. Cool, Savon, thank you for hanging out. Everyone's good to have you here. We'll have a fun plan for tomorrow. We'll get things going. If you have any ideas or recommendations, join the Discord. Pop them in here. And yet, code void. Greetings, scientists all over the realms. May the coming orbit of your chronocycles bring optimal outcomes, high energy experiences, and minimal system errors. Yep, that's a happy New Year's from Code Void there. Thank you, happy. Let's see. So say, thank you, happy New Year's to you too. Party popper. Okay. Hey, Michael Prince, how's it going? Yeah, interested in the fundamentals? Really? Okay. So that's something else that we could do. We could just walk through some of the fundamentals. We could do like, easy, like make it really easy and chill, like just walking through some of the basics. And we can do a whole basics series in Python to get more people up to speed. So we could do basics series. It's like really simple things, like variables and strings, and then arrays. We do things like that, and then how you manipulate them and how you access them and what you do with them. Then we could do like for loops and list comprehension and while loops, if else, right? We could do those things. We could maybe do some agnostic fundamentals, like language agnostic fundamentals. So I think Python is actually the best for that. I'd be happy to do it in any other language, though you would have to get over some of the challenges. A lot of people like programming language basics, not really agnostic, so heap allocation and stuff like that. Oh, hey, Jing Wang, thank you for subscribing. Welcome on in. Good to have you here. Yeah, we might do some fundamentals here as well. I think that's been a common request. So Jing Wang, if you didn't know, I'm Stephen Blum, CTO at PubNub. We've got a globally distributed infrastructure where devices connect in for built-in app communication. We power a lot of things on the internet. We're connected on your phone. We're connected on your TV. We're connected on your laptop. We're connected everywhere. We're fully connected. And we've been doing this for many years. I've been in tech for 25 years. We've got over 1 billion connected devices. I've got a lot of patents. I'm happy to tell you what worked for me. So thank you for joining. We'll be talking a lot of source code, walkthroughs, starters, AI, a lot of focus on AI. It's fun to do it in C. Yeah, Neva, that's also a good idea. We could also do C, fundamentals in C. Since a lot of people, C. Yeah, C. Okay, we could do C. I like C. We could do C. That one's great. Let's do it. Let's do a C. All right, so maybe we'll do some C fundamentals, like pointers, basic variables, stacks, heaps, allocations, mallocs, deallocs. Thank you for the likes, you guys. Thank you for all the reactions. K&R, what's K&R? Threads. Oh, there's no UI on these glasses. Really? It sounds like on the phone. Thank you for the reactions. You guys saw the party poppers come in there. I think I also send a book in the Discord that covers them in depth. Nice. Okay. So maybe implement a shell in C. Oh, we like a shell, like bash. We could do that. I think we could do that too. That's also more advanced, although not too advanced. It would require capturing standard input. It's called, I think, Programmer's Perspective on Computer Systems. Nice. Kernel module or kernel module. Ooh, there we go. There we go. Let's build a kernel module. That sounds like a good one. We could do that too. We can get some heavy stuff. There's a lot of ideas, Savon. Thank you. Yeah, exactly. Yum, haha. All right. Parsing is kind of ridiculously long to write. Might be too annoying. It is. Yeah, it's a good point, right? User input, parsing user input does require a lot of consideration, especially, yeah, it sure does. You know it does. What's K&R? I missed that. What's K&R? I miss embedding development, Steven. Did you? Well, you mean like microprocessors and those sorts of things? AI era 8, all that. It did. Yeah, we're in a whole new world now. Code generation. We're in a whole new world of code generation. Okay, so maybe we could do some C fundamentals and some Python fundamentals. Yes, sounds good. Yeah, the AI era is what you're describing. Yep. All right, everyone. Thank you for joining. We're headed out now. Good to have you here. We'll be back tomorrow, and maybe KNR is the first book on C. Oh, is it? That basically it stands for hot miboot. Hot miboot. All right. Is a required leading in a lot of universities. Got it. Okay. Good to know. Hey, Neymar. Hey, Neymar. Hey, how's it going? It's good to see you. We're just about headed out here. It was good to have you stop by. We'll be back tomorrow, and we'll be doing some fundamentals. I think. Is you good? We is good. Ricci and Carrot. Oh, okay. Got it. Okay, yeah. I thought we'd do agnostic in C. Most books are written in C. Yeah, we could do C. We'll do C. C is great because there's only a few, like, what do you call it? The keywords. C is really easy. Bye, everyone. Yep. Good to see ya. We'll be back tomorrow. We'll be doing some fundamentals in C. We'll bring our own compiler. We'll do it all by hand with no, C would be lovely. Nice. We'll be doing C. I love C. My technology at my company, our message bus, is written in C. I wrote it. It's in production. Trillions of messages goes over my network every month with billions of connected devices, or a billion devices. Yeah. I think we should also optionally in your course. Oh, all right. Sounds good, everyone. All right. Code Void. Thank you again for, you don't know anyone here for most part, and so the time zones. You're going to wish people a New Year at one time? I know, right? It's New Year at one time or another. Happy New Year, everyone. Yay, agnostic basics in C. Let's do it. We'll do it. Agnostic basics in C. Sounds good to me. And then help me along the way too. If there's anything we want to cover or any additional like things that we missed, like fill in the details. We can fill in the details. So that'll be the plan. That'll be planned for tomorrow. All right, everyone. Thank you for the hearts and the likes on the stream. Appreciate it. We'll be back tomorrow. Good to see ya. Happy New Year. Bye, everybody.